All right, so we'll begin in about 30 seconds or so. Let me get everything situated over here. Get all this text off the screen. Mhm. Okay. Oh, I had an announcement, but now I can't remember what it was. Something about speaking in front of an audience, it's harder to remember stuff. That's why I always have to write down all my notes. But, um, right. Oh, right. I think I wanted to announce that this was going to be at least the last in this series of linear algebra videos I make. I'll probably come back to linear algebra. We haven't done any sort of orthogonality stuff, or yeah, really like the second half of Axler. So yeah, those just joining us for the first time, I see Afro, two O's. So we're working on linear algebra. We've been doing, I think this is like my seventh or eighth video, and yeah, we're gonna transition into some probability statistics, like some stochastic processes things. I want to kind of talk about it's. I mean, you could think of it as financial mathematics, but I like of thinking of it as like a little bit broader than just that sense. You could think of like random processes other than financial mathematics, of course, if you don't like the money part of it. But hello, everyone. So yeah, let's get into the material. Change of basis. Where's my markers? Yeah. So 3D and Axler, he has a lot of stuff in here. I kind of skip most of it, honestly. It's not that it's not important, but I want to really just focus on the most important parts of it. Of course, because I don't have like unlimited time to go over the entire book. So yeah, he talks about invertibility in this chapter, and one of the main topics when you talk about invertibility is a change of basis. That's basically every invertible map from a vector space to itself is some sort of change of basis. So yeah, so I wanted to start at the change of basis formula, and in Axler we really specify everything, right? When we write down a matrix, we say it's the matrix of a transformation, and then we specify both of the bases. Um, so here, yeah. I'm just gonna basically write down everything very explicitly for this formula, and this is 3.84. So 3D, 3.84, and this is really your change of basis formula. Right. So here it says if you have the matrix of the transformation in one coordinate system, so we'll call that A. So if A is this matrix of T with respect to this U basis, right, T is just some map from V to itself, linear map. So we write down the matrix in the coordinates with respect to this basis. Remember, so that means that like we send each basis vector through the transformation, and then we write down what the linear combination of these vectors is that gets that whatever that result is in V. Right, so it's basically like the columns are a bunch of coordinate vectors. The coordinate vectors are the coordinates of where the map T sends all of these basis vectors. And then we could also write down B, which is the matrix of T in a different coordinate system, which is like maybe some V1 through Vn, right? And then your natural question is like, what's the relationship between the two? And if I know one of them, how do I change basis to get to the other one? So in other words, what is the formula basically that relates these two matrices? let's go. You checking the weather here? Okay, so that's kind of what's going on here. So what does the change of basis formula say? It says we have this matrix in one coordinate system. We want to change to a different coordinate system. And there is some matrix, invertible matrix, that changes from one basis to the other. So what does the formula say? Okay, so A is this matrix, B is this matrix. Also, I left out C. So C is our change of basis matrix. And the important thing here is that A and B are the matrix of T, but this change of basis matrix is actually just the matrix of the identity transformation. But the key here is that you're viewing it with respect to the domain and codomain. Even though they're the same vector space, you're viewing it with respect to a different set of bases. So one is going to be U, and the other one is going to be V. So the first one is U. Oops. Yeah. Right, meaning that we plug in U into the identity map, and then we write each vector U in the coordinate system that's made up by the VIs. So basically, we just want to know what are the coordinates of U1 in this basis, what are the coordinates of U2 in this basis, and etc. And also, I'm leaving out another matrix, which is the inverse of C, but the inverse of C is basically this same matrix, but we swap these two bases. So it would be the V's first and then the U's. And yeah, I would say that the most, like if you're a student taking this class, the number one thing that you'll mess up in computations probably is that you're just going to get not that you're going to get the wrong matrix. Well, you will get the wrong matrix, but a lot of the times people switch these, and so they'll be computing C as C inverse, or vice versa, however you want to think of it. And so in the end, when they use this formula I'm about to write, they put C where C inverse is supposed to be, and then they put C inverse where C is supposed to be. So what is the formula that relates the two matrices? The formula is that A is equal to the product C inverse B C. So this is a matrix product. Okay. Hopefully you can read that, right? Right. So, yeah, we have the matrix of the transformation in one coordinate system, different coordinate system. We have the matrix that is the change of basis matrix, and then the formula says that A can be written as a product of B with this change of basis and the inverse of the change of basis matrix. And another way to write this formula is you can move the C and the C inverse to the other side, and you could also say that B is equal to, and this is where I say to be careful that the C's are in the right position, but it's C inverse first, then A, then we do C. So C inverse, then A, then C. Okay, are there any questions about the formula? So I think it's pretty straightforward, but yeah, we'll do a 3x3 example in a second that hopefully will make this more clear if the formula is confusing you here. But yeah, I would suggest if you are confused, probably, if you're watching the video in the future, probably just pause it and make sure you understand, like, how do we get these matrices, and also why might this formula make sense? Yeah, non-commutativity, right? These are non-commutative. It's a good point by Rex. So if they were commutative, right, then C and C inverse would cancel, but they're not. They're not commutative, of course. Okay. Right. So let's do an example of Let's do an example of a linear transformation. So an operator, a linear transformation from some vector space to itself, and then we'll write down the matrix in two different coordinate systems, and we'll write down a change of basis matrix, and we'll just check that the formula is true. Hope everyone's having a good Friday. End of the week. Okay, so let's write down. So one of the linear maps in Axler that he keeps coming back to is you have this polynomial space, and you can take derivatives, like calculus derivative. And we know from calculus that the derivative of a polynomial is a polynomial of one less degree, right? So our first example, I just came up with this. I guarantee Axler probably has, if not this identical problem, something very similar to this, but I just came up with this on the spot. So this is the differential map, which sends, well, it's really just the derivative. So this maps to itself, P2, so polynomials of degree 2 or less, mapping to itself. So if I take the derivative of a degree 2 polynomial, it's going to be degree 1, right? Degree 1 is going to be degree 0, so this map makes sense. So, right, I take a polynomial, and I map it to the derivative, which is also a polynomial. And we know from calculus that this map is a linear map, and now I can write down what's the matrix of this linear map once I fix a coordinate basis, or really two bases, right? So one basis of the u's I could write down as 1x squared. So first basis, another basis. So actually, I guess this would be a whole nother problem to actually check that these are bases, right? But let's just assume we're past that. We've already figured out that we've checked that these are actually two bases. So 1 plus x, and 1 plus x squared. Okay, so, I mean, you could probably do this problem a couple different ways, but the way I'm going to do it, not that I've actually stated a problem yet, but I'm going to basically just be demonstrating that the change of basis formula is true. What we're going to do is we're going to write down the matrix with respect to this first basis. We're going to write down the change of basis matrix. Yeah, we're going to compute the inverse, and then we're going to figure out what the matrix is with respect to this other basis by just using the formula and multiplying out the matrices. Right, so what is the, I guess let me change the marker for a second. So what is the matrix of this transformation with respect to this first basis here? That's what we wanted to try to figure out. And so remember, I guess we can recall what the definition of the matrix is with respect to a basis. So A is going to be made up of column vectors, which are the coordinates of the image of the map under the image of the basis vectors under the linear map. So we're just going to take the derivative of each of these, and then we're going to write it as a linear combination of these, and the coordinates of that linear combination, that's what's going to go in the columns of the matrix. So basically I just send 1 through, I take the derivative of 1. So yeah, what's the derivatives of these guys? And what's the coordinates? So I take the derivative of 1, I write it in this coordinate system. I take the derivative of x, I write it in this coordinate system. And then I take the derivative of x squared, and I also write it in this coordinate system. All right, let's go. I know it's hard because I can't really see who's thinking. I don't want to wait too long, but so 0, 1, 2x. Yeah, that's the derivatives. That's correct. But now, so not only do we want to take the derivative of each basis vector, but we want to write that derivative in the coordinate system given by that same basis. So that's our definition of A. If you go back to the last slide. So yeah, that is correct. LL Gaz. 0, 1, and 2x. But now we want to know what is the coordinates of 0 in this coordinate system. In this basis. I'll let you guys think about it for a second. I'll go on a coffee break. Yeah, 0, 0, 0. That's the first one. Yeah. Right. So we take the derivative of 1, we get 0, and that's 0 times 1 plus 0 times x plus 0 times x squared. So the first column will be 0, 0, 0, as Rex just said. The answer is pi. Yeah, but you spelled pi wrong. That's blasphemy. You can't spell pi that way. This coffee is really good. I got some at like Starbucks, the ready-made ones. Probably too much sugar, but nobody can figure out the coordinates here? Okay, so I'll do the next one. So we take the derivative of x, right? We get 1, but that's just 1 times the first vector plus 0 times the second vector plus 0 times the third vector, right? So we plug in the second basis vector, and the coordinates we get for the result is 1, 0, 0. Yeah, 1 times 1, 0, 0. Yep. Right? Well, it's not really 1 time. Well, technically you're right, but I think you're using the 1 times incorrectly, probably. At least in your head, maybe. The coordinates are just 1, 0, 0, so we don't need to like multiply it by anything. Yeah, yep, perfect. Thank you, new chatter. 0, 2, 0, yep. Yeah, that's the last one. Yep, x squared. Take the derivative of x squared. We get 2x, which is 0 times the first vector plus 2 times the second vector plus 0 times the last vector. So that is correct. 0, 2, 0. Okay, so if you're following along and doing this on paper or something, let's just keep track of that this is A, and now we're going to try to figure out, so what is the matrix B, which is the same transformation, but viewed in this second coordinate system. So you can kind of think of it as you like squished, so you have R3. If you want to think of it visually, you could think of you have like 3-dimensional space, and you could like stretch one of the directions, or you could shear it a certain way. And yeah, just essentially you're dealing with the same dimensional space, but you're viewing the coordinates a slightly skewed or squished way. So in this coordinate system, you could think of this as kind of like the standard coordinate system. This would be some sort of like slightly sheared coordinate system, and that's going to affect what this matrix is in this other coordinate system. What Stooky waiting? Okay, so yeah, we have A here. I have it on my paper, but if you're following along, you could just write it down or something. And now we're going to try to figure out what is the change of basis matrix between these two bases, and then we're going to multiply everything out to try to get the matrix B. Gaz, G-A-Z-Z. Okay, yeah, so I think that looks, what did I get? This is for C, you're saying? LL Gaz? I'll just call you Gaz. Yeah, I think that's what I got for, oh no, that's, oh, are you talking about B? Yeah, that's the final answer. Yeah. 0, 0, 0, 1, 0, 0. No. I have something slightly different, I think. One, two. Yeah, I think I have something slightly different. Let's do it out, though. 0, 1, 0. Yeah, we'll see what we get. So this is A. Let's write down the change of basis matrix here. I probably wrote all this stuff too big. Probably should have wrote it in the corner, but okay. I'll copy it. Let's leave this here. We're gonna rewrite everything once we do the multiplication out, anyways. So. Okay, let me just copy everything here. So these are the two bases. So we have 1x, x squared. This was the u's. The one we're changing into was 1 plus x, 1 plus x squared. The first matrix A was 0, 0, 0, 1, 0, 0, 0, 2, 0. Now we're trying to figure out what is C. What is this change of basis matrix? Thank you for banning the bot. Welcome, Zach. Welcome to the mod team. So we have A here. So what is the change of basis matrix? So we're gonna remember we're writing the coordinate vectors, we're writing the vectors from the first basis U in the coordinate system of the second basis, these V's here. So basically what we're asking is, the first column is going to be, the question we're asking ourselves is, how do we write 1 as a linear combination of these basis vectors? And remember that the coordinates are unique. So we know that if we have one solution, that's the unique solution. So it's 1 times the first vector plus 0 plus 0. Right? That gives us 1. And then to get x, it's actually -1 times the first vector plus the second vector, plus 1 times the second vector. So the second column is going to be -1, 1, 0. And then the last basis vector, x squared, here is a linear combination, which is 0 plus -1 times this plus +1 times the last vector. So the last column is 0 times the first vector, -1 times the second, plus 1 times the last. So that gives us our change of basis matrix C here. Okay. I'm trying to think of, so I think I just threw it into Wolfram Alpha and it gave me the C inverse. But this one's actually very easy to compute the inverse. You can do what we did on Wednesday, which is, write an augmented matrix with the identity matrix on the right, and then you do all of your row operations. So I just don't want to, because I don't want to waste all the board space, but you could compute the inverse of this very easily because there's a lot of zeros here and it's already upper triangular. But just to save time here and writing, I'm just going to write down the inverse matrix. But I did want to stress that it's not very hard to compute if you wanted to just compute it by hand. So the inverse is 1, 0, 0. Oh wait, I'm writing the wrong one. That's the regular one. Yeah, it's actually all ones. Upper triangular, all one matrix. Yeah, there is a second board. I have some stuff in the way though right now, and I don't know. I'm just really loving this new board, so I don't know if I can even go back to the old board. All right. So we have our change of basis matrix, and we cleverly computed the inverse by not going to Wolfram alpha, but. So we have our inverse, we have C, we have A, so now all we have to do is apply the formula. So the formula said that A was equal to C inverse BC, or that B was equal to C B C inverse. And so obviously we're going to use this second version. Yeah, I'm really not good at saving this board space. I'll improve on. I think I've always had this problem, honestly, but yeah, I want to make things like spread out enough so that it's clear, but then I always run out of space too early, of course. So yeah, we're just gonna do this multiplication. I guess if you're watching the video in the future, you could pause and write down these matrices. Well, we're gonna write them down in the product anyways, so you'll see them again. But these are the three matrices. Now we just have to take their product. But again, remember that, like Rex said, it's non-commutative algebra here we're doing. So the order of these obviously matters. In fact, if you move the C inverse to be next to the C, then you're not really going to be computing anything because the C inverse and the C will cancel. So wallpaper, I'll just wallpaper the whole house. Or whatever this is called, wallpaper board. Okay, yeah, so let's just do the hard work of actually computing this product. And actually, it's not so bad because there's a lot of zeros in these, but yeah, I mean, if it was 4x4, it would be worse as well. But okay, I'll leave up the bases so that we can, at the end, we can check that our answer actually makes sense with this basis. Just to, you know, a little bit of a sanity check, I guess, at the end. Okay, so, right, so we're doing out our product. So here is B is equal to the product of these matrices. One, 0, 0, 0, 0, 2, 0. Yeah, and then here's the upper triangular with all the ones. All right. Oh, my arm's tired just writing all the numbers. What is this? Yeah, 27 numbers? No. Yeah, 9 plus 9 plus 9. Okay. So how do we multiply matrices? The way in Axler that he suggests, well, I mean, there's one way where you can do each individual entry as like a dot product of a certain row, the ith row and the jth column, basically. Or another way to think of it is, so if we're multiplying, let's just focus on these two matrices first. And so when you're multiplying two matrices, first of all, you know, you need the certain rows and column dimensions to match up, but if they're square and they're the same dimension, then that's already automatically satisfied. So we know that there are 3x3 and a 3x3 can be multiplied, that's fine. And so the way in Axler that's equivalent to the dot product way I was just suggesting is you take the first column, or whatever column you're working in, you go one column at a time of this matrix on the right, and you're going to take this linear combination of now I'm confusing myself, of the columns here. Yeah. So for instance, like the first column of the product here, the first column of the product of these two matrices is going to be 1 times the first column plus 0 times the second column plus 0 times the third column. And that will give us this first column here. So 1 times the 0 vector is 0. 0 times this is 0 plus 0 times this is 0. So the first column is 0, 0, 0. Likewise, 1 times the first column plus 1 times the second column gives us 1, 0, 0. And 1 times the first column plus 1 times the second column plus 1 times the third column gives us 1, 2, 0. Or like I was saying, you could view these, you could do the computation for individual elements, like by taking a dot product of the first row and the first column. That will give you the first entry. Second row, first column gives you this 2, 1 entry, etc. So I think the dot product way probably usually takes like way longer, but I guess depending on the matrices, it could be simpler to do in your head by doing each one individually. But if you have like a lot of zeros, for instance, like here, it was pretty easy to do this product in your head. Yeah. I like to do it both ways. I guess, I mean, they are equivalent. It doesn't really matter which way you do it, but depending on the problem, sometimes it's easier to just think of it as a linear combination of the columns. Yeah. Okay, so we get this matrix. This is the product of these. We have this first guy here. Now we just need to figure out what this product is. And it turns out that this operation is actually associative, so it doesn't matter if I multiply the first two together first and then multiply out the last ones, or if I multiply the way I did here. Associativity says that we should get the same thing, right? And I guess it's not actually completely obvious that the matrix multiplication is associative, except for the fact that we know that they represent these linear maps, and we know that functions are associative. Function composition is. So you actually get some very interesting results in linear algebra about matrices because they represent functions, but they're not like functions themselves. They have like interesting properties, such as like the determinant is multiplicative. This associativity of the matrix product comes from that as well. So some interesting results just from the fact that the matrices are in some sense representing functions, but they're not really like functions themselves. So you get kind of like these properties left over from that. Okay, and then let's just do this final product out just to finish the problem. I know it's a lot of multiplication. They don't change the final order. Yeah. You don't want to change the order of this product either, but you can change the grouping of the associativity. Okay, so finally, 0 times the first column plus 0 times the second column plus 0 times the third column, so this is just 0, 0, 0. 1 times the first plus 0, 0, so 1, 0, 0. And then 1 times the first column plus 2 times the second column plus 0, so the 1's cancel. Oh, wait. I might have done it wrong on my notes. Wait. Yeah, I think I did it wrong in my notes. Okay, so, oh no, I had it right? So 1 times the first, plus 2 times the second, right. Yeah, so -1, 2, and 0. right? Because it's 1 plus 2 times negative 1. So 1 minus 2 is negative 1. And then 2 times, yeah, 2 here is 2. Yeah, okay, this is right. I think this is right. If anyone sees an error here, let me know. But this should be B. And so let's just make sure that this matrix makes sense. So how do we check our answer here, or how do we keep some sanity that all the computation we did here is correct? Well, this should be the matrix of taking the derivative with respect to looking at things in this coordinate system, the second coordinate system here. So what we can do is we can actually just take the derivative of each of the basis vectors here and see if the coordinates of the results here make sense with that basis system. So if I take the derivative of 1, I do get 0 times this plus 0 times this plus 0 times this. So the first column makes sense. If I take the derivative of 1 plus x, I get 1. So that's 1 times the first plus 0. So the second column makes sense. And if I take the derivative of the last basis vector, I get 1 plus 2x squared. I get 1 plus 2x, which is negative 1 times the first vector plus 2 times the second vector, because the negative 1 and the plus 2 cancels to just give 1 plus x. So yeah, it seems like this answer does make sense. Yeah, exactly, GG. So good to check your answer here. I mean, of course, it's always good to just do the arithmetic correctly from the beginning, but you know, we're not perfect, so definitely if you're doing this on a test or something, it's good to check that the answer that you get at the end makes sense with what the problem's asking. Okay, so that is a fun change of basis problem. Yeah, and there's actually, so there's usually infinitely many bases we could view this problem. So you think of the transformation as happening in some sort of like coordinate independent way, and you can fix a basis and look at it with respect to the transformation with respect to that basis, but there's always, a whole space of different bases that you could pick. And if you pick different bases, then you have to change basis to figure out what the matrix will look like in that other coordinate system. Okay, I'm going to go on to another problem. So this is, I'm still in section 3D in Axler. Any questions about this before we go on? Yeah, so we're going over linear algebra right now, but next week we're going to transition into some statistics, probability, maybe like an introduction, some very simple stochastic processes type thing. Like you imagine, you have a stock price, or any random process that might go up or down with some probability, and you want to look at what that does over some history or something. So modeling random processes, really, I mean, we'll start with simple stuff like flipping a coin. You flip a coin, if the coin's heads, stock goes up. If the coin's tails, stock goes down, something like that. Yeah, stochastics. I mean, we could get into some stochastic calculus stuff, but I think it's actually more important to probably just go over like the simple stuff before we go into like stochastic calculus. It looks all fancy and cool, but I think some of the ideas in the simpler stuff is very important, and you don't actually need to go into the super complicated. Yeah, Markov chains. Yeah, exactly. Markov chains are a great example of like a simple stochastic process where you just have a matrix that's determining where the process goes in the next step, but each step is random, so it can jump around to different states, stuff like that. Yeah, random walks. Yeah, these are all stuff we want to talk about, exactly. Okay, so let's go on to this problem. Alright, so this one I'm actually going to do, it's just going to be one long proof, but I think the proof is somewhat illuminating, and the result is also interesting as well. So this is problem 3 in Axler in this 3E. Or, sorry, this is, I think I'm still in 3D, yeah. So 3D, problem 3, what are these questions? Yeah, definitely share some Markov chain questions with me, but I think probably I'm not going to start at Markov chains. I'm going to start even simpler than that, but yeah, I'll probably get to that within a week or so. Oh wait, are you even talking to me? Maybe you're talking to another chatter. Okay, so problem 3, so suppose V is finite dimensional. Finite dimensional vector space. And T is an operator on the space, so it's in the space of linear maps from V to itself. And then we want to prove that the following are equivalent. And the statements are, I'll try to fit everything here. So T is invertible. The second statement is that if I take any basis V1 through Vn for V, then TV1 through TVn is a basis as well. So TV1 through TVn is a basis for every basis V1 through Vn. And C is that same statement, but for some, there just exists at least one basis where it's true. So basically, same statement, but just that there exists at least one basis where this is true. So obviously, B implies C, because if B is true for every basis, then it's true for at least one, right? So B implies C is basically for free. But we want to prove that A implies B, B implies C, and then C implies A, so that they all imply each other, that they're all equivalent. Yeah, the following are equivalent. Okay, so we're first going to prove that if T is invertible, we're going to assume T is actually, I think I prove it by, how do I prove this? I can't even remember. Yeah, I prove it by contradiction. So we're going to assume T is invertible, and then we're going to assume that B is not true. So we're going to assume there's some basis of VIs such that T of VIs doesn't form a basis once we send the vectors through the transformation. So let's start writing this out. So assume T is invertible. Yeah, the following are equivalent. Yeah, you'll see this a lot. Just sometimes there'll be like 8 statements, especially in linear algebra. There seems to be a lot of these statements where it'll be like, the following are equivalent. T is invertible, T is injective, T is surjective, stuff like that. Okay, so assume T is invertible. Oh, sorry, I said we're going to go by contradiction. So assume T is invertible, and then assume there exists some basis such that TV1 through TVn is not a basis. Assume there exists some list V1 through Vn a basis with TV1 through TVN not a basis. Okay, so basically we just want to derive a contradiction here. So yeah, what do you guys think the argument, how should we argue, how do we get a contradiction here? So essentially we want to get a contradiction with something about t being invertible. Also, maybe I'm cheating a little bit here because I didn't go over something earlier that's in some sense necessary, but it does follow from the rank nullity theorem, so you could maybe come up with it on your own, or maybe you've seen this before, but or actually let me fill in the blank that I'm being a little deceptive about. So there's a earlier part of the chapter that says that there's, actually I said it before, there's an equivalence between if you have a linear map from a vector space to another one of the same dimension and it's finite dimensional, then t being invertible is actually equivalent to t being both surjective and injective. So if I know that I have a linear map and it's an operator on a space, it's from a vector space to itself, and I know that it's invertible, that's actually equivalent to it being injective and equivalent to it being surjective, meaning that if it's injective, then it's automatically invertible, or if it's surjective, then it's automatically invertible as well. So really, that's kind of what we want to get a contradiction with. The fact that t is invertible means that it's automatically injective, and now we want to prove that assuming this actually proves that it's not injective. So the fact that there exists this basis with, when I plug in the basis vectors into t and it's not a basis, what does that mean about this list? Can anybody tell me? What can we conclude about this list? If it's not a basis, what must be true about it? I know Stu probably knows. Stu Keep probably knows, but yeah, linear dependence. So how do we justify that? That is definitely what I was getting at. So how, if this is not a basis, how do we automatically know it's dependent? Maybe it's just some linearly independent list that's not a basis, right? Why is that not possible? And let me just remind everybody that a basis is a set that is both at the same time linearly independent and it's a spanning set, meaning that every vector in the space can be written as some linear combination of those vectors. So Zach says that they're linearly dependent, which is true, but I want to maybe try to justify that with something. So yeah, let's just write that down. So that implies that this list TVI is dependent list. But let's try to give this some sort of justification. So yeah, because there are lists that are not bases that are linearly independent, right? I mean, I could always just take a non-zero vector, put it into a list, and it'll be linearly independent, but it won't necessarily span the whole space, right? But here it actually is implied that this list is dependent, but I want like some sort of justification. Well, I'll maybe let you guys think about that for a second. And hopefully I'm not leaving out too much here, but obviously V is n-dimensional if we have a list of n vectors and we're assuming it's a basis. So the dimension of the vector space is definitely n. We assumed it's finite dimensional. Ooh, this coffee's really good coffee. I guess maybe I'm asking for a little bit too much here because I probably skipped over a little bit too much of the couple of the previous sections, but I guess the real important part here is that this list is already the correct size to be a basis, right? So there's n vectors in the list. If it was linearly independent, it would automatically be a basis because it's the right size, because we have a theorem that says if we have a linearly independent list, it can always be extended to be a basis. But if it's already the right size to be a basis, then that would mean it would extend by no vectors. It would already be a basis. So the key here is that there's actually already n vectors here. So it's the correct size to be a basis. And if we're assuming it's not a basis, the only way that's possible is if it's dependent. Because if they were linearly independent, then it would be a basis because it has the right size. Probably repeating myself here, but yeah. So essentially it just comes down to the size of this list. It's the correct size. The fact that it's not a basis must imply that they must be dependent. So if they're dependent, that means there's some linear combination that's 0. So there exists some AIs such that A1TV1, ANTVN is 0. And if this is the case, now I can pull everything, because T is linear, I can pull all of this stuff into T. I can pull all the scalars into T, and I can, the sum splits under T. So this is really just saying that T of this linear combination is 0. Oh, and also that they're not all 0 here. The AIs are not all 0. That's very important. So the fact that it's a dependent list means that there's a non-trivial linear combination. Non-trivial meaning that not all the AIs are 0, such that this linear combination is 0. And now the linearity tells us that we can pull everything inside of T. And now it says that T of some non-zero vector is 0. And we know the vector in here is non-zero because not all the AIs are 0 and the VIs are a basis. So the only way to get the 0 vector is if all the AIs are 0. So we have some non-zero vector mapping to 0, and that means that T is actually not invertible because the null space is non-trivial. So this is a contradiction here. I'll take a different marker. Okay, does anyone have any questions? So that just proves the first part, that A implies B, because we assumed A and we assumed the negation of B, and we got this contradiction. We got that T actually wasn't invertible because T is not injective. Something non-zero gets mapped to 0, and we know that 0 always goes to 0, so two things map to the same thing, not injective, not invertible. Any questions? Theory always scared me. Yeah, but it's not really too bad here. I mean, this is a pretty interesting statement though, right? It's just saying all we're assuming is T is invertible, and automatically we get that it moves around bases to bases. So every basis gets mapped to some other basis. In fact, we assumed here that if it mapped one basis to something that wasn't a basis, then it automatically couldn't be injective. It couldn't be invertible. So a little bit scary, but it's a very powerful statement because of how broad and abstract it applies to any vector space, any invertible map, and we automatically get every basis is automatically guaranteed to be sent to a different basis. So, and then like we said, B implies C. This is easy, right? Because if it's true for every basis, then it's true for at least one basis. So really what we want to do now is prove C implies A. And then we'll be done because A implies B, B implies C, obviously, and then if C implies A, then everything is equivalent. Everything, each statement implies each other statement. Okay. So any questions before I go on here? Yeah, that's actually a very good way of thinking of it, Rex. That's the way I was thinking of it before. It means we collapsed at least. Yeah, it means that essentially if the map is not invertible, then there's at least a one-dimensional null space. So at least one non-zero vector gets mapped to 0, and then every multiple of that vector also maps to 0. So there's some at least one-dimensional space in the null space, if assuming that T is not invertible. And so contrapositive would say, if T is invertible, then the null space is always 0-dimensional. Okay, so let's prove this last statement now. So we're going to assume that for some basis, there exists one basis where T of V1 through T of Vn is a basis for V, and then we want to show that that implies that automatically T is invertible. So this was A implies B, B implies C is easy, and now we're going to prove C implies A. So this will be C implies A. Okay, so we're going to assume C. So assume there's some basis. So assume there exists V1 through Vn, a basis for V, such that T V1 through T Vn is also a basis. Yeah, Rex, exactly to put it simply, yeah. Yeah, that's actually a very good way of thinking of it, Rex. We're collapsing at least a one-dimensional space to 0 and sort of ignoring it in the image, and it gets erased, and the rank nullity theorem says that the image must sort of be missing that dimension. So whatever dimension the null space is, the image is missing that amount of dimension. Okay, so C implies A, so assume there exists a basis that gets sent to a different basis by T. So we have V1 through Vn as a basis, and also T V1 through T Vn is also a basis. So we want to show that T is invertible. Right. So in order to show T is invertible, we can show that the null space of T is 0. So that's equivalent to T being injective and equivalent to T being invertible. So essentially what we want to do is show that T of anything is, if we assume that T of something is 0, then that something must automatically be 0. So assume T of A1, V1, blah, 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 and Vn is 0. So because the VI's are a basis, I can write any vector in V as some linear combination of them. So this right here, if the AI's are arbitrary, this represents any vector in V, depending on what the AI's are. So assume that this is 0. We want to show that this is automatically 0, but we can rewrite this as A1. It's basically the same linearity property that we used for the last proof. We can pull all the constants out and split the sum. So it'll be A1 t of v1, a2 t of v2, all the way through an t of vn is 0. But then we assumed that the t of vi's were a basis, so if this is 0, that automatically implies all the ai's are 0. And that means that the original vector had to be 0, and so the null space is just 0. So because these are linearly independent, that means that all the ai's are 0 for all I. And that means that this vector in the middle here that we plugged in originally, we assumed it could be arbitrary to begin with, but then actually if t of that was 0, it actually implied that all the ai's had to be 0. So really, the only thing that we can plug in here to get 0 is the 0 vector, and that means that the null space is 0, and that's if and only if, for an operator, t is invertible. Because injectivity and surjectivity, like I was saying at the beginning, are equivalent to invertibility if the dimensions are equivalent on the domain and the codomain, which is always true for an operator. Operator is just another term for a map from V to itself. Okay, so I'm running out of room here a little bit, but the whole argument is here, right? So we assumed that there exists some basis where the transformation sends it to another basis. So VI's are a basis, the T of VI's are also a basis. And then we wanted to show that the null space was 0 to show that T is invertible, and to show that we assumed that T of something in V was 0. And we used the linearity property to split it, and we used the linear independence of the T of VI's to say that all of the AI's had to be 0. And therefore, because all the AI's had to be 0, the only vector that we can plug in here to get 0 is when all the AI's are 0, which is the 0 vector. So the null space of T is the 0 vector. That means that T is injective, and that implies that T is invertible. So from C, we imply A, and that's everything. So A implies B implies C trivially, and we just showed that T implies A, so everything is equivalent. So A implies B, A implies C, C implies B, C implies A. They all imply each other. Okay, so that's a fun proof. Oh, I'm going long here. Okay, I got one more though. This next one's pretty easy. Yeah, we'll do one more quick problem. I guess there's no reason I need to stick to an hour video. I don't know why I've been sticking to exactly an hour. But yeah, are there any questions about this proof? So it's 3 statements. We showed they're all equivalent to each other, meaning that if any one of them is true, then all the other ones are true. If any one of them is false, then all the other ones are false as well. Every time I say AI? Yeah, I mean, I can do more time, but I figured, well, no, 3 hours is a little bit long. I'll definitely get tired for 3 hours. At least if I'm doing like this type of stuff. I'll figure out something that works. I don't want to do too much on one topic, though. I think that's the thing. Like, if I was going to do two hours in a day, I'd probably want to do like 2 separate topics or something. I'm not sure. I'll think about it. Right, so then I just wanted to do one more problem from this section before we go, which is number 11. But yeah, if you have any questions about this, definitely drop them in the chat. And I need that chill hop music going on to stall the silence, or to end the silence. Yeah, see, Afro's already tired now. You can't go 3 hours. Math is tough, exactly. So this is number 11. Same section, this is 3D. It says supposed V is finite dimensional again. Finite dimensional. And we have two linear maps, S and T, from V to itself. So linear operators on V. And we want to prove that the composition ST is invertible if and only if S is invertible and T is invertible. So they have to both separately be invertible, and then that's equivalent to the composition being invertible, meaning that if the composition is invertible, then they're both individually invertible, and vice versa. If they're both individually invertible, then the composition is invertible. But I think one direction is super easy. So which direction is easier to prove here? Like which, assuming which one and then proving which one. Do I assume the top one and prove the bottom one first? Which one's the easier of the two to prove? Get a different marker. We're all AI. I'm the first AI math tutor on Twitch. This is all AI. This is all a social experiment. So which one's easier? Need a countdown timer. We're talking about the Matrix, right? Yeah. I think it's the up way is easier, right? Yeah. Yeah, assuming this is true and this is true. The composition, I think, is obvious that it's invertible, right? Is that clear to everybody? That if S is an invertible map and T is invertible, meaning they're both injective and surjective, then if I compose the two maps, then it's also injective and surjective, right? So, yeah, I mean, two things can't map to the same thing under T, and then they also can't map to the same thing under S, so the composition is injective. Similarly, you can show the composition is surjective. So I think this way is pretty, showing this direction is easy. So let's just show the other direction. Right, is anybody confused about this direction going up? Like assume these are both injective and surjective, and then you show the composition is both injective and surjective as well. All right, so yeah, I guess just stop me if you're confused about this way, but now we'll prove the other way. So let's assume ST is invertible. Okay. And like I was saying before, to check invertibility of a linear map is equivalent to checking injectivity, or also equivalent to checking surjectivity, which, because we're dealing with linear maps, is other language we can use is that we're checking the null space and the range. We want to check that the null space is 0, and we want to check that the range is the entire space, whatever vector space we're dealing with here. so we're going to assume ST is invertible. So that's going to imply oh, right. Actually, no. Let's prove it by contrapositive, I think, is actually probably easier. Yeah, I mean, there's probably a way to write it out this way too, but well, I mean, if it's a true statement, there has to be some way to write it out, right? But so let's assume the contrapositive, or we're going to prove by the contrapositive. So I'm going to assume that this is not true, the bottom statement. So assume S is not invertible or that T is not invertible. So we're just going to do a, what's it called? Proof by part. What is this called? Proof by cases, right? So there's two possible cases, right? Either it's the case, if we're assuming that the conclusion is not true, then it's either the case that S is not invertible or it's the case that T is not invertible. So we'll just assume one and we'll prove that ST is not invertible, and we'll assume the other one and we'll prove the same thing. So let's call this number one, and we'll call this statement number two. So first we'll assume one. And so if S is not invertible, that means that the range of S is not equal to V, and that means that the range of the composition is not equal to V. So range of S is not equal to V, and that implies that the range of ST is not equal to V. Right, so ST is not surjective, right? Because if the map S is not surjective, there's no way the composition can be surjective, because, you know, T is just hitting things in V, and once we map to S, there's something that doesn't get hit. So in the composition, there's still something that doesn't get hit, so the range of ST is not equal to V, and that means that ST is not invertible. So that's basically all we had to show for that one. And now I'm running out of room here, but maybe I can fit it. So assume this second one, assume that T is not invertible. That means that the null space of T is not zero, and same thing with the composition. So very, very similar argument, but now for the null space. So null T is not equal to 0. And that means that the null space of the composition is not equal to 0. So sorry, I'm running out of room here, but it's essentially the same argument I just made for the range of S, but now we're working with the null space. So the null space of T is not 0. That means the null space of the composition is not 0, and that means that ST is not invertible. So in either case, if we assume S is not invertible, we get that the composition is not invertible. If we assume T is not invertible, we also get that the composition is not invertible. Other direction's easy, so we proved this way, we proved the other way, and now that means that these two statements are equivalent to each other. So there's no way for the composition to be invertible and not both individual linear maps also be invertible. Okay, so I think this was my longest stream so far, so congratulations to anybody that's still here, and I think we'll end it right here. I'll probably ship it off to anybody that's doing math currently. I'm not sure if NSimplex is on, or maybe Zach is streaming already by now. Who should we send it over to, Rex? Oh, Stu. Okay, yeah, definitely. Yeah, I didn't know he was streaming. They were streaming. Okay. It's just Ian Stuckey, right? Yeah. Let me stop